What I'm about to show you is one of the hardest IMO shortlist problems of all time. It doesn't have an official rating because it's an IMO shortlist, but most people agree on it to be a 50 moles problem. 50 moles meaning that it's borderline unsuitable for the IMO. And yet this is also one of the most high quality grid combi problems that I've ever done. And it showcases a unique insight into how powerful forcing moves can be. This is a problem that not everyone talks about. In fact, few people actually understand how elegant it is because they either fail to solve it or read a solution that doesn't showcase its beauty. I'm talking about IMO Shortlist 2017 C8. Here's the problem statement. Let n be a given positive integer. In the Cartesian plane, each lattice point with non-negative coordinates initially contains a butterfly, and there are no other butterflies. The neighborhood of a lattice point C consists of all lattice points within the axis aligned 2n plus 1 times 2n plus 1 squared centered at C, apart from C itself. We call a butterfly lonely, crowded, or comfortable, depending on whether the number of butterflies in its neighborhood n is respectively less than, greater than, or equal to half of the number of lattice points in n. Every minute, all lonely butterflies fly away simultaneously. This process goes on for as long as there are any lonely butterflies. Assuming that the process eventually stops, determine the number of comfortable butterflies at the final state. So the first question that I had when I tackled this problem is, does the order of butterflies leaving matter? And second of all, does it actually terminate? I mean, the problem tells us that this process terminates, right? But we still cannot be sure if it actually terminates or not, and by understanding why it can actually terminate, it might give us a clue or two about how to solve this problem. I mean, to prove that it terminates at one point, we don't have to create the final configuration, right? We just need a suboptimal construction that shows that there's a boundary that these butterflies cannot cross. So let's start with the idea of order. So if you look at the problem, they tell you that each minute every butterfly that's lonely will simultaneously fly away, right? But can we remove the butterflies one by one? Turns out that we can actually, because by removing one butterfly, you are not affecting the loneliness of other butterflies. As in, like, if one butterfly starts out as lonely and you remove one other butterfly, that butterfly is not going to convert back. So with this in mind, we know that we can remove them in any order we want, as far as by the time we remove a certain butterfly, it is already lonely. So how do we manipulate the order to our advantage? The first thing we can do is symmetry. We know that this process has to be symmetrical because, well, the lattice grid is. So it's safe to assume that the remaining configuration will be some kind of curve that's also symmetrical with respect to the y equals x line as well. But before we think about a curve, there's one specific manipulation of the order of butterflies that can help us a lot. And that specific manipulation is that we want the shape of the lonely butterfly that had left in any point in time to form a staircase. To make the idea of a staircase more rigorous, we can define it as a set of lattice points with positive integer coordinates, such that if a certain point is in that set, then the point below it and the point to the left of it, if they also have positive integer coordinates, it will be in this set. This is how we can define a staircase. So how does this help us? Well, it helps us because if at one point in time this is the configuration of the butterflies that had left, this might not be possible. I am just going to set up one possible configuration and say this one can be removed. We don't care what n is, say that this one can be removed for now. Observe that since the configuration of the butterflies that had left is a staircase, if you go down like this, you only encounter more empty seats, as in, like, you only encounter more empty lattice points without butterflies. So if this one is lonely, then when you move it down, this one will have even less butterflies in its neighborhood, or an equal number of butterflies, so it also has to be lonely. And therefore we can move it down like this until it hits one of the columns that we drew here. But this also fails to create a staircase because we can still go to the left. But the same logic applies here, so we can use the inductive hypothesis to move this one to the left, right? And what happens here is that now it forms a staircase again. Now we have a set of butterflies that have been removed, a set of anti-coordinates that forms a staircase with one more point. So we can assume that the ending configuration, the final state of the butterflies, will have the empty spots forming a staircase. But what kind of staircase would it be? Here is the thing. I've listed out the full configuration for n equals 2, and this is what you're going to get. These are all empty coordinates these butterflies have left. So the first observation is that it's symmetric, but also the trend of butterflies seem to follow some kind of curve. And if we think closer, this should hold for bigger values of n as well, although they have to be bigger curves, and the gradient has to change very slowly. We cannot have tight turns like this, because if we look at the neighborhood of some butterfly along this line, as in like at that sharp turn, you look at its neighborhood and you realize that less than 50% of it is covered with butterflies. But if we try to force the entire thing from the leftmost and bottom, as in like the bottommost butterfly in the leftmost column, you'll see that this idea fails for one reason. If you look at this specific butterfly and you forget about this entire configuration, you look at its neighborhood, you see that it is forced. The position of these butterflies is forced. So you think to yourself, oh, it should be forced for all of the other points then, right? Unfortunately, this is not the case for this one. If we look at this one, we cannot force anything from this, because now its neighborhood shifts down like this, and the thing is that we can place a butterfly in 2 spots, but we only have to place 1. This is the start of the issue. It loses its forcing quality, and as this process goes on for larger values of n, we cannot force anything, and yet there's only one single optimal final configuration. This failure motivates us to look at the final product instead. This is the core idea. Instead of trying to force everything out through a process, we will look at the end product immediately, as in like we will skip time ahead and look at the end product and force everything from there. Observe that I said earlier that this process has to be symmetric. It is symmetric about the line y equals x. So this also motivates us to look at the butterflies with the lowest y plus x coordinates, as in like if we draw these lines over here, or we can think of it as moving this y plus x equals 0 line upwards until it hits one of the butterflies. And we look at the leftmost butterfly among the set of butterflies that it first hits. You'll see that regardless of how large n is, let's even say n equals, let's say n equals 3. This is what we are going to have. These are empty. Like this entire area cannot have any butterflies. No butterflies, no butterflies. And we can see that there are only half of the total spots left. So whatever happens at the point is forced. We can know about its entire neighborhood just from swiping this line across the board. But can't we do this with other lines as well? Because if we swipe a different line across the board and you let it hit a certain point, as in like you consider the first point that it hits, it is going to bisect its neighborhood into two parts with an equal number of lattice points in it. What happens is that you can rotate it so there are an equal number of lattice points on each side, and you know that on this side right here, there are no butterflies. And so we can consider this kind of process for every single line, and we can force so many things about the final configuration. So what lines do we use? Which lines are going to be relevant to us? Well, let's come back to the n equals 2 configuration. What I'm drawing here is the convex hull of the final configuration. You'll see that if we draw this line with slope -2 over here, and we swipe it, it's going to hit this point first, and so this point is forced. But also, if we draw this kind of line, the line with slope -1/2, and we swipe it right like this, it's going to hit this one first. And by looking at the neighborhood of this one, we also know which butterflies have to be there, right? And so this motivates the following idea. We are going to swipe every single line that goes through 2 points in an n+1 times n+1 lattice rectangle with no lattice square. What I mean by this is, in case n equals 3, we are going to consider every single line here. And what happens is that when we enlarge this line, we swipe it like this, we can consider the neighborhood of the butterfly that this line hits. What happens here is that the configuration here is forced, because you cannot have any butterflies above this point, but also everything in this half has to be filled. So what we're essentially saying here is that we can force the existence of every single segment in here on the convex hull of the remaining butterflies. Okay, but at this point you might be asking, what does this idea even do? Why are we trying to force segments on the final configuration? Does this prove optimality? Does this even prove existence? Does it prove that this works? Well, it does both actually. And this is what I mean by that. If we look at all of these lines, you know that we can slide it across the plane and force the existence of, say, this segment, right? I'm just going to use a larger pen. We want to force this segment, and so we can slide this line over here until it hits this point. And this is what we are going to get. We can also slide this one. I'm just going to enlarge it. This one has slope 1/2. So this is what we're going to see here. We slide it across the plane, and it's going to hit this one first. So we can draw this segment as well. And with the red line, we can also draw this segment. See, this is what I'm talking about in terms of like forcing everything on the final product. But how do we prove that this actually works? Well, we can look at an example. In this example, we see that the line that will hit this point first in the convex hull is this one, the line perpendicular to y equals x. But as we look at this line, we see that there's one point missing, which is this one. It is missing from the neighborhood, but we are going to prove that this cannot happen. And the way we do that is that we consider the convex hull once again. This point is missing, right? We are going to draw a line connecting the missing point to the butterfly that we are inquiring about. You'll see that it has to intersect our broken line at some point, and we will consider just this broken segments of the blue line. Notice that the gradients on the last segment here has to be greater than that of the orange segment over here, which means that the orange segment has to be within this green section of our broken line, which is not possible because this orange segment has a greater difference in y coordinates than this entire segment does. So there is no way it can fit into this segment. You can even use geometry to disprove it. You can even use like obtuse triangle side length properties to deduce that this segment cannot lie within the part of the broken line defined by these two intersections. So as we've proven this for the points on the convex hull, how do we prove the same for points not on the convex hull? More specifically, how do we prove that all the other points are crowded? Well, we are going to associate them to a point or a segment on the convex hull. This is what I mean. I'm drawing this y equals x line because this is going to determine how we do it. Say we are selecting some random points over here above the y equals x line. I'm going to draw the line parallel to the x-axis through this point and see what it cuts. I will divide this into two cases. Firstly, it cuts a point, and second, it cuts the middle of a segment. In case that it cuts a point, this case is easy because we can look at the neighborhood of the points right here. As this point moves to this direction, we can see that the number of how do we say this? The number of empty spots in this neighborhood decreases because you can shift this entire broken line to the right, this way. And the number of points within this one's neighborhood, let's call it A. I keep having a brain block, sorry. The number of butterflies within A's neighborhood that stays within this second broken line that we drew is already half of the number of possible slots in the neighborhood. And it even has some other butterflies outside of this half. Therefore, it has to be crowded. Let's visualize it so that it can be more clear. This is what I mean. The number of butterflies in this area is already enough to make this one comfortable, and it even has extra points outside, therefore it has to be crowded. Now let's look at the second case. The second case is that our point does not get associated with a point, but rather with a segment. It cuts through the middle of a segment. Well, we are going to prove that it is crowded only for the point that is closest to that segment, because it is already the strongest case. Proving it for this point, we'll also prove it for this one, and so on. So the first observation we can make is that P and Q must be inside this guy's neighborhood. Let's say that this segment contains k points. The gist of this is that if we draw a parallel line to this, let's draw it in pink. If we draw a parallel line to PQ passing through our point of interest, let's call it A, but I'm not going to write it here because the diagram is already a mess. The points in A's neighborhood that lies above the pink line is the same as the number of points in P's neighborhood lying above the red line. But the difference is that P is going to have at most k minus 1 other points in its neighborhood, but our point A is going to have at least k. What I mean by this is that if we consider the upper boundary of P's neighborhood, the lower boundary of Q's neighborhood, and then we extend the line PQ to meet these two lines, every single lattice point to the right of this line is occupied. Since all of them are occupied, we can safely assume that everything to the right or on the pink line is also occupied, since it's basically a translation of our previous line, right? But the thing is that when we count the number of points on or below the pink line for the neighborhood of A, I'll just label it for now. This one we call it A. The number of butterflies on the pink line or below in the neighborhood of A is at least one more than the same thing for P and Q. Therefore, it has to be crowded. And the only comfortable butterflies in the whole configuration are the ones that are right on the convex hull. And this allows us to biject every single point on the convex hull of this curve right here back to this square that we drew. So this one, I'm going to label it like this: 4, 5, 6, 7, 8, 9, 10. This is where it goes. We can do this bijection because we have already forced the existence of every single segment on here, and any other construction will clearly create a larger difference between the y coordinates of the top point and the bottom point. Therefore, this one has to be optimal, and we can conclude from this bijection over here that there are exactly n squared plus 1 comfortable butterflies in the final configuration. There are so many things that you can learn from this problem, but for this video I'm going to mention 3 of them that I personally found very important. The first one is about learning from failed ideas. This is a concept that I had already touched on in my IMO 2011 P4 video and also my anti-Pascal video. But in this case, it's not enough to look at the failed idea and ask what applications or what adjustments can I make to the idea to make it work. Sometimes the idea fails because of the nature of the approach itself. In this case, our idea to force the entire curve from top to bottom failed because as we go down the curve, the forcing effect of the butterflies decrease. What I mean by this is that we cannot force the optimal construction out of just this process alone. And if we look deeper into this issue, we will see that not every butterfly has the same level of forcing effect. And which butterflies are going to have the most forcing effect? Well, that motivates us drawing the convex hull, because that's how we can really define the outermost butterflies, right? If a butterfly is on the convex hull, then at least half of the area of its neighborhood is gone. So we need to make sure that in the extra area that is gone, there are no lattice points on it. The second takeaway for me is that you need to find a structure that creates a forcing effect. It's the same that I just said. You draw the convex hull because you want to reduce the amount of data that you have to deal with and focus on what actually matters in the problem, in the setup that you're dealing with. Like, we're not going to care about that random points in the interior of the entire structure, right? We want something that's more prone towards breaking the entire setup. The last takeaway from me is something from personal experience. I did this problem as a break from studying biology for an exam. It's just some backstory that I need to tell first. I was really tired from all the memorizing and I just needed to do some math to take a break. I knew this problem was at least 45 moles just by looking at it. It just has the aura of a hard problem. And so I had no expectations of solving this problem. I was just letting my curiosity lead. And then I found the area about using a line to cut through a neighborhood and divide it into two parts. And I was like, wait, we can do this with other lines as well. We are not restricted to the line perpendicular to y equals x. So what if we just import the line from 2022 C9 and swipe it across the board? Well, it turns out that we can actually do that, and we can force every single segment on the convex hull, simply because we trusted our curiosity to pursue the idea of a line bisecting the region further. I took only an hour on this problem, and that should say a lot because this is a 50 moles, and I've never solved something of this difficulty this fast before in my entire life. And the reason I managed to do this is because I had peace of mind. I was not under any expectations, any pressures. I was doing this because I wanted to have fun with the problem. And this is what I want you guys to be doing. As I said in the previous video about psychology in Math Olympiad, you need to be free from internal distractions, from external expectations and all sorts of pressures. You just have to focus on having fun with the problem in hand. Thank you all for watching and see you guys in the next episode.